Okay, the stage is all yours.
Excellent. Thank you. Good evening, everyone. Thanks for coming and thanks for your interest in this talk. I'm Rajan. My background is in electronics and hardware, as you heard. But today's talk is perhaps closer to a scientific Python. In a way, I've been a paper reviewer for that conference. That was a volunteer thing. Today, I strive to interest you in this color measurement or exploring color using Python. I reckon you're all tired after a day of work, so I'll keep it simple. But feel free to interrupt me at any point in time. If I can answer your questions, I'll be happy to do so. I've organized my presentation in roughly 3 different chunks. I hope I'll take 10 minutes each. First one may take a little longer. I will just go through basic color measurement ideas as they're prevalent today. But primarily we are looking at the Python color science package, and I'll be using some of it for demonstrating how we do things for color measurement in it. And the last part of the presentation is about the hardware that goes with capturing spectra, which is what feeds this package and does rest of the processing. So if you have any questions along the way, feel free to interrupt me. Now, it's almost impossible to do justice to a color measurement topic in 10 minutes, but I'll try. There are a bunch of packages I have loaded over here, no particular dependence or such that I have worried about, but it just works. So best way to start is dive straight in to talk about how we specify color. Let me make it fit the screen. So you can see all the axes. So this is how we specify color on this XY diagram called the CIE Chromaticity XY coordinates. And I'll start explaining this and then we'll go back to why it looks the way it looks. What you have here is, call it tongue-shaped locus, and I mean, some people call it horseshoe shape, but it looks more like a tongue to me. There's a red dot in the center. That's what we call the equal energy white, and we'll come to it once again later. On the periphery of this curve, or the outer edge, what you see is these numbers from 390, it seems, to 700. These are the wavelengths of this color of light. If you look at the spectrum, you know that the colors vary from violet to red, and those are the wavelengths that are associated with those colors. So outer edge of this particular curve is what we call this spectral colors. Okay? The line that you see over here, this magenta line, there's no wavelength that can stimulate the eye to perceive that color. We have to mix those 2 colors over here. And any color in the middle over here, it can be realized by a combination of spectral colors, and we'll go through it. So colors are specified in terms of X and Y coordinates in this diagram, and given XY coordinate uniquely specify chromaticity. Now, why does this curve look like this? For that, we'll have to go back to an experiment that was done somewhere in 1931 with few test subjects. And I'll go through how we arrived at this curve by this experiment. So color matching experiment. This was done to match 3 primaries, red, green, and blue, with spectral colors. By that time, I think it was understood that we could additively combine various colors and generate metameric colors. When you combine colors, you can generate other color sensation, combine three primary colors in this manner. You could generate other colors. So this experiment was done in this manner. We had a test object over here, which was illuminated on one side by a spectral color, and on the other side we had three primaries, red, green, and blue, which were combined in various ratios to match that color. And these RGB values then became the tri-stimulus values. So you'll hear this term often, tri-stimulus. What does that mean? That's where it comes from. So essentially, it gave three coordinates, if you may, red, green, and blue, various ratios in which red, green, and blue could be combined to achieve another spectral color. Is this clear? Okay. Now, at that point in time, when this experiment was done in about 1920s, 30s, we did understand a little bit about the structure of the eye, but the rods and cones and correlating those with the kind of response that you get from this experiment came only later. So there was later on, it was shown there is a very good physical basis for these for this experiment to be done in this way, and the result that comes out of this experiment. There's a little bit of physics here, if you may. This is what it looked like. So colors were matched, and after matching RGB components of those colors, they were normalized. And after normalization, we obtained this kind of colors. Now, what this kind of curves? What does this mean? So this shows on the x-axis different wavelengths, and on the y-axis the the RGB values required in the ratios in which they are required to combine to achieve that color. Okay, so this RGB color matching functions became the starting point for the CIE X and Y that we saw on the first diagram. However, there was a little bit of if you may say, something which is counterintuitive. You see the red values goes negative, and that didn't make sense. How could you match a negative color to achieve another spectral color? It will become clear later on how this negative value came about. But this, amongst other factors, was one of the reasons that a transformation was carried out from RGB to XYZ. And this was purely an algebraic transformation to get rid of that behavior of negative color, of negative red. And with that algebraic transformation, we obtained this kind of XYZ curves or color matching functions. And these became the basis of the small x, small y that we saw on the first diagram. XYZ are in a way were derived by a simple linear combination of RGB. There's a fixed matrix conversion that is involved over here. But in the process, there was something else clever that was done. This green curve, which was matched to the response, so spectral response of the human eye to different wavelengths. So this green curve also matches the photopic curve, as they call it. Okay. The XYZ color matching functions became the basis to define what we call the XYZ color space. So if every color is specified in values of XYZ, you get a three-dimensional cube, but it is somewhat difficult to work with, to send a cube and coordinates to printers and dyeing people and cloth manufacturers and say this is where the color should be. So instead, to make it easier, a simple technique was used to use the projection of those XYZ values on this unit plane. So the diagram that you see is essentially projection of those XYZ or intercept of those XYZ values on the unit plane. And that's how that curve looks like. So when we did that, we ended up with a curve like this. So that locus of points is essentially every spectral wavelength where it intersects the unit plane, and the colors are indicated for convenience. So those are all spectral colors, and inside all this locus of points is different metameric colors that you can form with the white, equal energy white as they call it, in the middle. So finally, this is the shape that we ended up with the CIE Chromaticity Diagram. The only detail left is the small x and the small y, which was simply a normalization of x, y, and z values where small x is x plus y plus z, x over x plus y plus z. So those normalized values are then indicated over here. Now, yes. This curve that you see is the 111 plane, basically, on the three-dimensional solid. This is the 111 plane. This is where the intercept, where the XYZ value intersects the, if you extend the vector, this is where it will intersect the unity plane. So that's okay. Yeah. You took words from my mouth. No? That's exactly where it is. So these triangles, sRGB from Microsoft and Adobe RGB, is what we call the color gamut. Anything inside this color gamut is what that particular color scheme can realize. So obviously, these 3 points are then called, primaries, or 3 primaries for that particular color, and any combination, linear combination of those primaries will allow you to achieve this. So when you go to buy a monitor or a printer, in addition to paying for size, you should pay for gamut. Larger gamut you have, the more vivid your colors would be. And that's kind of the value of looking at the CIE color diagram. It allows you to compare color reproduction capability of a printer or a monitor or a display or a device like that.
So if your source image specifies a color that's outside the gamut, it will get clipped.
This is what happens today in the coding schemes already. Yeah. So a printer is a subset of this sRGB. A printer in general cannot accomplish all these colors truly. The laser displays have a wider gamut than our LCD monitors, and they cost a lot more. I'll also point out that human eye is capable of roughly, we believe, 380 to 360. I think 380 to 760. When this data was done in 1931, this was the capability of the instrumentation. So these curves look like this, but it doesn't mean we can't go about 700. So just in case you have doubt. So I think with this, you have basically a good first cut idea of what color is, short of a couple of weeks of lecture about how color is measured. There are a few points I would like to highlight in case. So this experiment is a little bit tricky to perform. Done in 1931, there was you can say, a prism on one side with a 40-watt automotive lamp. Maybe the experimenters, Wright and Guild, had a car or something, so they used, and these are gelatin filters. And there was a vapor lamp on this side, opal lamp on this side, which was used to generate these RGB primaries. The values, so the other 2 things that are not obvious in this is white match. The first thing that was done was a white color was matched with these RGB primaries to set a reference value. So that was very important. So I mentioned the equal energy white in that diagram. Later on, that equal energy white was used as a reference. So a 1 unit of red and a 1 unit of green and a 1 unit of blue does not mean 1 watt of red and 1 watt of blue or 1 watt of green. They're different. And those weighting factors are also provided by the CIE. Right? So when I say we mix red, green, blue in equal proportions to get a white, it doesn't mean we use 1 watt of red and 1 watt of blue and 1 watt of green to get white. There are ratios. Okay? So that just keep that in mind. So oftentimes we will say when we look at this diagram, or maybe I go further down, that in order to synthesize yellow color, so if you look at the wavelength about 570-ish over here, equal amounts of red and green would give you a yellow. And this is typically how we articulate it. But when we actually do some experimentation, you'll find that we have to weight it. And roughly, it has to do with the luminosity of the sources as well as response of the human eye to different wavelengths. So there's a weighting involved. Okay, so I think we have enough about color and measurement of color. So next thing I want to look at is this color science package, and we have ability to explore some of these ideas in color science using this data structure. Here it's called the spectral distribution. So it gives us a way to just create artificially a spectrum. So it's an array of data from 380 to 760 with numbers, and it represents wavelength and amplitude of that particular wavelength. So in this case, I have synthesized with some weights over here. You can say 2 lasers. So there's a laser at 546 and 700. The one at 700 has an amplitude, relative amplitude of 72 point something. These numbers came from the CIE. And if you plot these spectral density, it looks like this. And if you plot this in the chromaticity diagram, both of these functions are all nicely encoded in the color science package. You can see that it falls somewhere here. So we are synthesizing a yellow color using unequal ratios of red and green. You can see it's slightly off, and I attribute that to the fact that I'm not using wavelengths with decimal places that the primaries are. But if you say, you know, why not just mix them in equal proportions? You know, what harm does that do? You'll see
So where the import is?
Okay, I have to go back and import this. I've done this. What color? There we go. So you have equal amplitudes of green and red, and you can see that the point shifts on the chromaticity locus closer to the green side. Okay, so this is just to make you aware of the fact that there are weighting factors when you look at coordinates in the chromaticity diagram, and then you try to reproduce those in physically or you know, through software, in color science package software. So let's look at a few more things. So clearly, I mean, you can synthesize in this way different kinds of sources, combine them in various ways, and explore them in terms of their chromaticity. How do they look like, right? Let's do another simple one. So this time, let's look at, we said equal energy white, right? Equal energy white means at every wavelength of interest, it has equal amplitude. Right? And we synthesize this with a spectral density all once. I have weighted it by 0.5. We can remove that weight later. And then there's a bunch of routines here to help you plot as well as visualize it. So you can see equal energy white has a chromaticity which is where it should be. The white spot, which is equal energy, we also call equal energy white. But in terms of looks, it looks grayish, right? It is definitely not white. So if I increase the amplitude here, let's make it 1. Oops. Now it looks more whitish. So the luminance part is not encoded in X and Y. It's only the chroma that is encoded over there. So that often does lead to encoding colors as XY and the big Y, because big Y is that information. Okay, you can have chromaticity the same as white, but the appearance will depend also on how luminous it is. Okay, let's make it 0. Equal energy white, where equal energy is, well, 0 or very small. It looks more like black, you know. So.
In the previous example, you showed sort of
700 nanometers.
Yeah, sorry, yeah, but the amplitude difference
of 70. Yes, yes.
70 for the one and 1 for the other, right?
1.2 something for the other. That's right. That's right.
But then here, in order to make white,
yes,
using
everybody is equal. This is so, you know, the as they call them metameric colors. You can synthesize colors by combining different wavelengths in different ratios. So in this case, the definition of equal energy white is that all wavelengths have the same energy content. They have the same amplitude, and that defines the equal energy white. That's also the white reference, not physically realizable, but that's the theoretical reference white from, let's say, National Physical Lab. Yeah. So when you're realizing white by combining red, green, and blue, you're creating a chromaticity of white metameric by those combinations, which is in a way simulating what a real equal energy white should be.
Okay.
Yeah.
I guess I'm confused why you wouldn't then still have to change the
ratios.
I'll
put it this way. The response of the human eye is to colors is by captured by the Y curve, right? So when I took only 3 primaries, or 2 for that matter, one was somewhere here, one was somewhere here, 700 here, and one was somewhere here. So the sensitivity of the eye is different, very little to blue, very little to green. So if I'm using those, the ratios would be determined by weighting of this function. Whereas I'm having every wavelength from here to here, the net sensation is different. Yeah, the weighting by the V lambda curve, as they call it, is the reason for it. It's a little more complicated. I've ignored the luminance of the RGB sources in the other case, but that's the idea. Okay, so we explored equal energy white. We looked at synthesizing metameric yellow by combining spectral colors green and red, and we have a notion of the weighting factors required to achieve the energy level to get the right ratio of colors. There are other primitives that are available in the color science package, and one of them is obviously LEDs. You know, various kind of luminaires are available. LED is one of them. So in this case, I synthesized a blue LED at a wavelength of 450 nanometers, which is bluish, as you can see over here. And LEDs, unlike lasers, they have a slightly broad response, right? The wavelengths have a spread. It's not very sharp, unlike a laser. So if you look at a LED data sheet, it will give you a number around 20, 25, 30, so somewhere around there. So I've just used it. For this primitive, it's a Gaussian profile. And if you put this to a spectrometer and capture the data, this is how it will look like, roughly. Right? Now let's look at this LED on the chromaticity diagram. And from the spectral distribution, color science package supports its transformation through a set of commands. And rightly, it's somewhere here where blue should be. I think I picked a 400 and what's the number there? 50. And that number is somewhere below 460. Somewhere below 460. So, okay, I think it's working. Now, on the chromaticity diagram, we have equal energy white over here. And if you join these 2 points together, you reach the other side, which is called the complementary color. Right? So now when we mix colors, as I mentioned, we can achieve chromaticities in the middle. So it should be possible to mix blue with yellow and achieve a white chromaticity. And that's what we'll explore next. So in this case, I have 3 LEDs. One is a pure blue, one is a pure yellow. I've chosen 570 for yellow color. And then there's a dual LED. In the market today, you can find one LED bulb with multiple emitting elements in there. So I've chosen dual. You can get triple as well, RGB types, and see what sort of chromaticity it shows. So I have, you can see relative amplitudes of those two are in the ratio 1:1.5. And when you plot that in the chromaticity diagram, you can see you can push this point closer to the white color. Just for reference, I have kept the blue point and the yellow point over here. So this is how you can manipulate different colors in a display by varying the relative intensity of different light emitting elements in there. Okay. Now we can explore if this can be varied. So if we make both of them equal, so these are relative powers of the two wavelengths. So if you make this equal, how does that look like? It's equal, and you can see the point is shifted little towards the blue side over here. In the same way, you can shift it a little towards the yellow side over there. Let's look at a few more. This is how does the color look like when viewed in the RGB color space, and this is how it looks like. I have increased the luminosity. You get a better looking white over there. If you turn it down, you'll start going towards tints of white. So next thing with white is to look at black body radiation. And as you know, for pure black body radiation, the spectrum is a function of the temperature, right? And these primitives allow you to explore that a little bit. So at 6,500, yeah. So at 6,500 Kelvin, you have a peak in the black body radiation, which is somewhere close to blue. And the color of the black body, as you vary the temperature from below 2000 to supernova temperature somewhere here, varies from reddish to white to blue. And this also forms the basis of the notion of correlated color temperature of a light bulb or something like that. So chromaticity of a bulb, how closely it matches the chromaticity of a black body radiation at a particular temperature becomes the color temperature specification of a light bulb. If you go and buy a Philips light bulb, you'll find there's some number: cool blue, warm yellow. I don't know what. The D65 is also the standard for average daylight, so it is kind of used as a reference in some of these color computations. So equal energy white is one reference point, which is theoretical, very hard to physically realize. You'll always have some spectral shape to things. It's never flat. So D65 is the next closest reference point that you use. We can look at some other lamps, such as a fluorescent lamp. In the chromaticity diagram. So again, since we're talking about black body radiation, what you see over here is a curve of different black body colors as it varies from, I think it's 200 2000 Kelvin over here, all the way going to supernova temperature over here, and the fluorescent lamp primitive that's available. These are spectra, these are data sets available in the color science package that have been sort of recorded or made available somehow and stored over there for you to play with. So fluorescent lamp FL1 is somewhere over here, and I think that's just one of the characteristics that is specified when you manufacture these kind of things. So so I think that's my last illustration on this topic. So this is a D65, and the illuminant D65 is the one which is typically used to represent average daylight, and you can see it's non-uniform spectral response and chromaticity of this. I leave it to you to look at the use the this particular S-patch S-watch command to see how it looks like. It will be white in color, but that's how you can explore this further. So I've just scratched the surface of what's available in color science package to explore color, and around color there are other things that are available in the package, such as whiteness, yellowness. If there are two chromaticity coordinates available, what is the energy difference between the two? So in some ways of finding the difference, and sort of how much do we adjust X and Y to achieve a target X and Y. Colorimetry is just one part of this package. There are other things available in it depending on your interest, biochemistries, so on and so forth. So I have not touched upon those, just scratch the surface of color measurement today. So this is all on this color science package, colorimetry methods that I want to mention today. If you have any questions on it, yeah. Yeah.
In other words, is it possible to achieve color resemblance by varying the luminosity of a point? Right. I asked this because I noticed you have light blue and dark blue on the same diagram.
Yeah.
I would presume that the former is a function of photon frequency, energy, and the latter is how many photons.
Yeah. So when you're dealing with human vision, the term that you use is photopic or radiometric when you're referring to watts, photons, and so forth. And I forget the name for the other one. So to answer your question, the given a spectral distribution of the energy source, it will always be shaped by the response of the eye. So you have to keep that in mind when you're talking about what we see versus what the instrument sees. Did I answer your question? So your question was, can you get the same color by simply varying luminosity, or same feeling of color by simply varying luminosity and not chromaticity? Is that what you're saying? I mean, the strict answer is no. But if you look at the, there are other formulations of X, Y, Z coordinates like LAB and UV and HSV and so on and so forth. So towards, as you increase one of the like luminosity, they seem to be looking almost the same, but it's not, chromaticity wise, they're not quite the same. Yeah.
Physically, they are
Yeah.
biologically.
Human eye is not a very reliable instrument. The brain and eye do wonders in ways. So what looks like color A may look like slightly different color A to you if the surroundings are different. We know those things, right? So okay, so now we're ready to go to part 3, and this is more related to hardware. I mean, we've worked with the assumption that a spectral distribution was available to us. Either we synthesized it through a data array, and then we could do the other things. We could ask other questions. What is the chromaticity? What is the correlated color temperature? What is the whiteness? What is the color rendering index? There are all kinds of performance measures available to characterize sources of light, and not just sources of light. It could be a filter which transmits light. It could be a reflecting surface, like everywhere, that reflects light, where in addition to spectrum of the light source, you have reflectivity of the object or transmissivity of the filter to put into that multiplication summation formula to get the x, y, and z, right? So but nevertheless, our starting point in every case is the spectral distribution, right? So how do we get that spectral distribution? We get it through a spectrometer, but that's not the only way. Just for completeness, there are these filters available, sort of pre-crafted X, Y, and Z. So you can have measurement cameras where there's an X filter in front, and the reading that you get is already the X value, right? So that's a sort of crude way of doing it. The more formal way or older way, I would say, is through a spectroscopy. And if you look under the hood, how do we get the spectrum? It's a very simple. Every one of you have studied in your physics class at some point. You have an entrance slit, you have a transmission grating, which breaks the light into different wavelengths, and you have an image sensor, which basically gives you at every wavelength what is the amplitude, and that's what you read. So in this part of the discussion, I'll just go through one of these kind of devices. Most of the devices, spectrometers out there in the market, will give you a XY comma separated value, or just array of some kind that you can fit into this package. For this particular device, it directly plugs into your USB port, and it gives you a class object that you can instantiate and then start capturing the signals. So this is roughly how the raw data looks like, and some of the processing that's done on the raw data before you get your XY, the wavelength and amplitude array. So one of the things variables to play with here is the integration time. So this is the exposure time of your camera. The longer you integrate, the larger signal you can accumulate. Also, it means you can saturate the sensor. Also, it means that a smaller signal can register with a larger integration time, subject to the noise floor of the device, or noise limits of the device. So first reading that you take in a camera device is a dark reading. You have no signal, no optical signal. You capture what's the spectra that you get, and you get something that looks like this. It's random noise, it's electrical noise, it's thermal noise, anything else, light leakage, everything will contribute to this baseline. So in this case, you can see this is a digitized value available over here. This device goes from high to low, so you're seeing from a 10-bit A to D converter a value around 800, right? It varies within plus minus 10, I think, or plus minus 5, but that sets our dark current reference. If the temperature goes high, this number will go high. If you cool the device, this number will. If the temperature goes high, the leakage current will go high, so the reading will go up. If the temperature cools down, this reading will come down. So after that, just a little bit about calibration, since we are looking into the device. So you connect a calibration light source. It tends to be a mercury argon or a gas lamp of some kind. And from your physics days, you'll remember that these lamps give discrete wavelengths. At discrete frequencies, they give peaks, right? So you capture these peaks, and you know what the wavelengths of these peaks are. So you can calibrate your pixel. And this device has about 1,500 pixels. So knowing that this wavelength is 435 nanometer, this is 546, you look at the chart. You know, the chart has this shape, so you know this is this one. So you can map your pixel axis to a wavelength axis, and that's probably the first step that you do. You determine the calibration coefficients by fitting this pixel position to wavelengths and sort of synthesizing a polynomial. In this case, I've used a NumPy polyfit function, just fed them the xy values and just synthesize a third order polynomial. You can go to higher orders. There's nothing limiting. It depends on the non-linearity in your device. At what point your coefficients, the higher order coefficients, start giving an insignificant contribution. If the contribution is less than 1 pixel, there's no point in having that coefficient. So in this case, it's just used value. And you can see this device at pixel 0 is 366.8 nanometer wavelength, and with every pixel is 0.28 something nanometer increment, right? And then there's a second order coefficient of 10 raised to the power minus 6 already going down. So when you remap the axis, you can see it starts matching roughly. So this is about 404. This is about 435, 546, blah, blah. You can see how good your matching is. Then we capture a, so once you've determined your calibration coefficients, you can capture an actual device. So this is an LED. This is the raw blue LED signal, how it looks like. There's always some noise in the system, maybe in this device a little bit higher than what you would like to, but still pretty decent. There's no mess of the type that you might encounter. You typically, first thing that you do is run some smoothing functions. In this case, there are many kinds of smoothing filters available. You can have Savitsky-Golay filter, percentile filter, simple convolution filters, rectangular, triangular. You can try what works best for you. You get a smooth looking waveform. Hopefully it's not degraded, your filter has not degraded the amplitude or introduced distortions of other kind. Then you will do some scaling. In our case, the scaling is to match the axis, the x-axis, the wavelength axis. You can also do it for the y-axis. The response of pixels, just like the human eye, is not a uniform response. It has some curvature that's available in the data sheet. You can adjust the y-axis as well, at least for the curvature of the pixels. Typically, you'll put a black body radiation and try to make sure you fit that black body curve and that temperature pretty accurately, but it's a lot tougher on the y-axis. And then finally, you might be interested in measuring the peak and the full width at half maximum, which is a way of specifying how wide the peak is, how narrow, how wide it is. So again, in Python, you can use some, in my case, I've used some functions available from Skippy, find peaks, and that works pretty fine. I think there's some junk that you have to reject. So this has a 479 nanometer peak over here with a 30 nanometer at half maximum. So it's about 29 point something, 30 nanometer band, which is about right. I mean, you look at the data sheet of these LEDs, these are the numbers you will find. So this, then you're ready to craft your spectral data array. There's some cleaning up you can do. You can plot the array and visualize it. So it shows green over here. This plot basically just paints the spectral colors under the curve. This is not the color of the LED, and the color of the LED, of course, you can use this color swatch function to see how the LED looks like, within the SGB matrix. If it's outside that SGB gamut, you would have difficulty. So it's bluish in color, and you can plot it in your chromaticity diagram. It's somewhere here. It's slightly off from the axis, unlike the laser thing that we synthesized earlier on. It is not sitting right at this point. I mean, first of all, there are components at different wavelengths over here, and generally, you end up with some residual signal which is not real from the other side too. So it tends to pull the point towards the other side a little bit. So there are these things to customize. Now, this is a visible signal, so visible range spectrometers have less of a problem if you're looking at near infrared signals, which are in let's say 1 micron to 1.5 micron. You tend to have more of these. The baseline itself may have a trend. If you're looking at Raman signals which integrate for a long time, you start getting trends. So there are other cleaning up of the data that's involved that I have not shown over here before you get your spectral data array that you can then take forward. So that's my last curve for today. If you have any questions.
Thank you.